name is Nitsan Wolnai, and I'm the author of Data-Oriented Design for Games, published by Manning Publications. You can check out the book. The link is in the description. You can even read the first chapter for free. What we're going to do in this video is we're going to make a survival/bullet haven game where we have a whole lot of enemies chasing us down. Not much happens right now except the enemies are going to move toward us and chase us down, and there are about 2,000, well, there's exactly 2,000 enemies right here chasing us down. Note that we are not using ECS for this video. This is pure data-oriented design. ECS is a little bit about ECS. It's a design pattern that just happens to fit some aspects of data-oriented design. You can even use ECS with object-oriented programming. The idea here is to understand what data-oriented design is and make a game that just using pure DoD and not any sort of design pattern, because design patterns are one size fits all solutions, and in games especially we have a lot of unique problems, and a big part of data-oriented design is also how we actually solve problems. So let's create a project. We'll create this project from scratch and dive right in, and we'll show you how to make a Unity game, a prototype, using data-oriented design. So we'll start off by, first we'll take our scene and we'll rename it into our main game scene. We're only going to have one scene. With data-oriented design, we really care about the memory and how we use memory and how objects are structured in memory. And a scene is just an object that holds data in memory. And so we're just gonna use one, and we'll use prefabs to load and unload data into memory. We have our camera, which is, we kind of need that to see our screen. We'll also create our game loop, an object called game. It's gonna have a script called game that is going to control our entire game loop. And we also need to have our game board where the gameplay actually happens. The game is like, you know, our main menu, a pause screen, game over, stuff like that. But the board is actually where the gameplay happens. If you think of it like a chess game, you can have a chess app where you can choose single player, multiplayer, different themes, I don't know what kind of music you want to play. But then you actually have the actual chessboard where the actual chess game is taking place. So for us, where the actual gameplay will take place, we're going to call that board. And we'll also add a script called board for that. And in board, we're going to have sprites. And let's go ahead and create one of these sprites. We're going to just use, actually we'll use a circle. We could use our own circle, but if Unity provides us with one, let's just use a Unity circle. It's just a texture that's circular. And so we have a circle. What we actually want to do is, this can be our player, and we want to really, always in data-oriented design, we want to separate things in a way where we can control one thing at a time. For example, in this case, we want our circle to be, it's too big right now. We want it to be small, like let's say 0.2. And that means that our scale here is 0.2. But with Unity, it's a lot easier if the scale is set to 1, because when you instantiate an object, you might not know what scale it is at, and I don't want to have to save the scale of 0.2 anywhere in our game. So what we're going to do is we're going to just actually create a parent. We'll call that the player, and this one is at scale 1, and then our circle, the actual visual representation of our player, is going to be a 0.2. And we can take the same thing again and call it an enemy. Let's just move it around a bit so it's somewhere else. and then we can color it red, and that'll be our bad, evil enemies that are chasing us down. And let's also change Unity's default color to something a little bit more interesting. To create many enemies, we're going to assume that our enemy is a prefab that we can instantiate. So let's create a prefabs folder, and we'll move our enemy there. We'll also create another folder called scripts and move our scripts into this one. And we don't really need the player here, the enemy here anymore. The player we can leave. We could also make it a script. We could also make it a prefab and instantiate it on load. At the same time, it's always going to be alive, at least for this game. When we have one day in the future, when we have many different players you can pick from, then we can move it into a prefab. And that is, for now, all we need to show a bunch of enemies on the screen and even move the player around. So let's start thinking about, let's start thinking about what kind of data do we need to actually make a survivor game. So we're gonna have in our scripts, we're gonna have a game data class. And this is going to hold all the data we need to actually run the game. And when we think about it, let's open it up and start thinking about what kind of data do we need here. First of all, it's just going to be a class holding data. So we don't care about mono behavior or any sort of functions. This is just a pure class holding data that we're going to use in our game. So we need things like to position our enemies on the screen, right? So we need vector2 of enemy position. And yeah, I don't want to use system numerics for vector2. I want the Unity's vector2. And we also need, we don't need enemy rotation like suggesting, but we do need a direction for the enemy to move. So we're going to create, and each one of these should actually be an array, because we're going to have a whole bunch of enemies moving around. And we also need to know for enemy velocity, we can just have them, we can have that set in a different place, where like that's data set in the balance, which is data that game designers say, oh, this type of enemy is moving this quickly, this other enemy is moving at this other velocity. So that's not something that might change during gameplay, at least for now in this our simple example. If we were having enemies actually change velocity as they're moving around, then we would add an array here. But to keep it simple, let's just not do that. And we need to control, to know which way our player is moving. And we don't need player position because our player is actually going to always be in the center of the screen. And as we move, we'll actually move all the enemies around it. So the player can always stay in the center of the screen. We just need to know which direction it's moving at. And also the speed at which the player is moving can also be set in our balance. So if you go back here, we have our game data, which is probably all we need, at least for now, to get a bunch of enemies on the screen moving around. Let's go to our board. If you remember, our game board is where the actual gameplay happens. And so we need to have our player, so we can why do we need our player? We might not even need it, but let's have it on there, just in case. So we're gonna have our player, and we're going to have our enemy prefab, which we'll use to allocate a pool of enemies. So we also need a pool of enemies. We also want to place, when we instantiate the enemy prefab into a new game object, we want to place it at a certain place in our hierarchy. So if you go back here to our scene, we have our sprites empty game object, and that can be our the transform parent for all our sprites. So when we instantiate a new enemy from our prefab over here, we will place it under the sprites game object. So if you go back here, we can also add a public transform sprite parent where we will place all our sprites. These are all going to be public, so we can assign them in the editor, and our pool does not have to be public, so we're just going to make it an m_enemy pool. That is probably what we need for now. We have our game loop, right? We have this game object here, which is running our game loop as a mono behavior, and we don't want our board to be controlled by Unity. We want to have as much control as possible over our game. And as part of that, we don't want to call the Unity functions like start and update. We want to choose ourselves when to call them and to have them driven by game, our game loop. So instead, we're going to have a function called init. Init, thank you. And we're going to have, this function will allocate the memory we need. It's called once, and will allocate all the memory we need to actually run the game. Similar to, you can think of it like the awake function. And we'll also have a show function, which you can think of it sort of like on enable, which says, hey, we want to show our board. And we'll have a tick function, which is something we call every frame. And the tick function will always take delta time, which is like dt. It's the same as time to delta time, but it'll be passed from game, so we can control it from there. Also, I don't actually know if time.delta time is, because C# has getters and setters, it is entirely possible that calling time.delta time might call some function. I don't know, I could look it up, but it's one of those things where every time you call a function that is given to you through Unity, you always have to wonder, what is this actually doing behind the scenes? And do we actually want to call this a bunch of times in our code, or do we want to cache the value once and call it again? So in this case, we're going to call time.delta time only here once in update, and then pass that value to board. At the same time, you can also even pass our own time. Maybe we want to have a fixed rate and control our own fixed rate and only pass, let's say, 1/60th of a second, like a fixed 60 FPS. That'll allow us to do that by just taking a dt, a delta time. Now, we talked a bit about, we obviously created this game data, but we also talked about having the balance data, which is the data set by game designers. It's set at tool time once, it never changes again. So let's go ahead and add that data as well, so we can see what we need there. So we're going to create another C# script called balance. And again, just a class holding our data. And if you don't know why these are classes and not structs, which a lot of people think that our own design is all about having a lot of structs, you should read the book. In our balance class, we already know that we need enemy velocity. Which is how fast the enemy will move. One day, if we have a lot of enemies, we'll have this as an array. But for now, we're only going to have one kind of enemy. And we also know we need the player velocity. So we know how fast the player is moving in relationship to the enemies. We also need to think about how many enemies are we actually going to have on the screen, like the maximum number of enemies we'll have on the screen. So let's also add and num enemies as well. And this balance both our game data and the balance are going to be held by our game object. So here we can do public game data and public balance, and we'll make both of these serializable, so we can edit them in the Unity editor. Well, we actually don't want to edit this one. We want to only edit our balance. And that means that now when we go to Unity, in our game, we have a balance, and we can say, hey, how many enemies do we actually want? And for now, just to make it kind of small, let's make it 50. And enemy velocity, let's set it to like 1, and player will be twice as fast, so 2. So you can actually like, run away and avoid enemies. And in our board, we're gonna set our player prefab. We're gonna set our player game object. We're gonna set our enemy prefab, and we're gonna set the sprite parent, so we can actually instantiate all our enemy pool here onto sprites. Now that we have this information, we can go back to board, and in our init, we can actually allocate our enemy pool. So our init function needs to take in our balance, so we know how many enemies we have, and then we can do enemy pool equals new game object balance.num enemies. Then we can actually loop over this. We can create a new game object and instantiate it from our enemy prefab, and we can place it in the sprite parent. Then we can take this this game object and place it into our pool, and we can set it to be active false for now. So we can show it. We can show maybe not all enemies at once. Either way, we don't want to do anything visually yet at this point. In show here, this is where we'll actually go ahead and show all our enemies. We'll place them in the right place and show them. We also, in init, we want to allocate the game data needed for playing the game. If we remember, here in game data, we have these arrays: enemy position and enemy direction, and we need to allocate them. We don't want to modify game data anywhere other than in a static function, a function that takes in data, modifies it or transforms it in some way, and then outputs something. In this case, we want a function that is going to take our game data, and the transformation will be allocating memory for everything that is needed to run the game, and the output will be that our arrays are now allocated. So to do that, we're going to create this logic class. And by the way, these are the only 5 classes, five C# scripts we need to get our own design game running, our simple survivor game. This is like the base of our architecture, is having these 5 scripts: the game, which is the loop; the board showing the game board; the balance, which is data created at tool time by designers, and it isn't modified during the gameplay; the game data, which is what changes during gameplay and describes how the game is shown; board will visually show it; and logic is actually how we change the game data. And this is a static class. It is not a mono behavior in any way. It just takes in data, transforms it, and outputs data. So for our first function, we're going to do, let's call it allocate game data. And it's going to take a game data in it, and that game data will get modified. And we also need to pass in the balance, so we know when we allocate these arrays, it will be based on data in the balance. So we have num enemies, and I think we have enemy direction too. So we want to call this, so we're going to call it up here. The first thing we'll do is we'll call allocate game data, and we'll pass in game data. So it means that our init function here needs to take in game data as well. So now our init function in our board takes in game data, takes in the balance, allocates it in logic, where it allocates the arrays for the game data, and then we allocate our enemy pool and instantiate all the enemies we're ever going to have in the game at this time. Now we need to think about let's keep working on our board, and then we'll see how game actually calls the board. We want to show our enemies somewhere on the board. What this means is that we are going to loop over our enemies. Now it means that again we have to pass in game data, take in game data and balance, and now we're gonna take every enemy and we're gonna position it to the enemy position in game data and set it to active true to actually show it on the screen. So we'll take our enemy pool, transform local position equals game data dot enemy position, and we will also take this now and do it set active to true. Now the thing is that we haven't actually set these enemy positions to anything. So it means that in logic, we need to have some sort of like start game, which sets our enemies to some sort of default position. So we go back into our logic and we add another function, and we'll call it start game. And again, we'll take in game data and balance because we want to change the enemy position and probably the direction for every enemy. So we have to know how many we have. Now, being a survivor game, we want our enemies to spawn off screen and then to rush at us. And if we're moving in a certain direction, because we're moving faster than the enemies can move, well, most of them at least, we want enemies to spawn based on the direction the player is moving. For now, let's not get into that complication. We just want to make sure we can see our enemies on the screen. So let's just spawn them in a square around our player, just so we can see that our enemy pool is working and all our enemies are showing up on the screen. So to do that, we're just going to go to loop over our enemies. And we will set the enemy position of each one to just a random value. And to decide how big it is, just so we can see, not actually for the gameplay, we'll go to our camera and we can see the size is 5. We can actually see right here, if we go to our player, if we move it all the way to the left, it's something between 2.8 to plus 2.8. So we can use, let's use 5 as, we'll have a square of 5 by 5 around the player. to spawn these enemies. So we'll do this times 5.0f, but we want it to actually be from negative 2.5 to plus 2.5, so we will lower 2.5 from that, and then we'll have the same thing. This is for the x, have the same thing for the y, and that'll allocate our enemies. And we want every enemy to, we want the direction. We want all the enemies to move toward the player. So the direction always needs to be, we can actually take the enemy position. For example, if we just take this, let's throw an enemy prefab in here, just for the hell of it. And it's right here. It's at 0.93, 1.4. But to move toward the player, the vector is actually going to be moving toward it. So this way, which is actually a normalized vector that is the opposite of what the position is right now. In this case, it would move in the negative x and the negative y, even though here it's positive and positive. If we were on this side, we're negative 1.21, negative 1.7, but we want to move in the positive x and the positive y. So the opposite is this. So what we'll do here is we'll actually set our enemy direction, our initial one at least, to be the opposite of the enemy position normalized. Even though we aren't even moving yet, because we haven't implemented our tick function yet. But this way we just have it correctly. And in theory, if we go here and hit play, nothing has happened because we did not connect anything to game. So we go back to game, and here we can actually, we want our board that we can link to. Our game data doesn't have to be public because it's not changing, and it would actually be helpful to allocate it like this, allocate actual class. This class we don't have to allocate because we actually allocated it by editing it in the Unity editor. One more bad thing about Unity, where you don't actually have to specifically allocate this class. It just magically does it because we edited it in the Unity editor. One more way Unity makes things complicated behind the scenes. And then in our start, we can do board.init, and we pass our game data and our balance, capital B, and then we can do, let's make a function called start game, and we'll call it from here. We can actually call this from wake, which is a better place to allocate memory. And we'll call start game from start, and here we'll call board.show. And this way our game loop is actually controlling everything. It controls the board. Obviously we don't have any menus or anything right now, so it goes directly from game into gameplay. But at some point we'll have the separation where we'll be in the main menu or the settings or some other menu, and the game hasn't started yet, so there's no real reason to actually call board at that time. And then if you go here, we'll go into our game, we will assign our board, and then if we play, we probably crashed or something. Nope, we didn't crash. Let's go back and see what we did. I think that we didn't call logic.startGame, which sets the position of every enemy. So then if you go back here, maybe now we'll see enemies all around us. And yay, we have 50 enemies that have spawned all around us in what is basically a square. Next, we'll have the enemies spawn outside the view in a circle. And then we can add some player movement and have the player move and have the enemies spawn based on the player moving. We can also have it, even before we do the player movement, maybe we'll have the enemies move. So we can have all these enemies chasing down on the player. So to move our enemies, we are obviously going to do that in logic. That's the only place we actually change game data, or we should change game data. So we're going to have our tick function in here. Our tick function is going to take in game data, so we can modify it, and the balance, so we know how many enemies we have. And we're going to run, what we'll do is, we will update the position of every enemy based on its direction, the delta time, and the velocity from balance. Okay, so what we want to do is we want to take our enemy position and we're going to make it, it's going to be the current enemy position plus the enemy direction times the enemy velocity times delta time. And that right there should move our enemies in a direction that was set, and which was toward the player. If we go back to our game now, we'll go, so this is logic. In board, we'll call logic.tick, and we need to pass the same thing. So we need to pass game data and balance. Game data, balance, delta time. And then we want to update the position of every enemy based on their new position. So let's just take the code from here and set the new position of every one of them. And in our game loop, we're going to call also board.tick, and we will pass in game data, balance, and time delta time. And now, let's go to our game and let's set our player velocity. In velocity is 1. Okay, let's see what happens. Absolutely nothing happened. Let's think why. We're in update. We have board.tick. Goes to the board, calls logic.tick, and which should set a new enemy position. So the easiest way to do it, to figure out what's going on, let's just debug it. Play the game. Go into our values. Go in here. We have 50 enemies. We have our enemy positions. We have our enemy directions, which are all set to 0. Why? Because right here we did enemy direction dot normalized instead of enemy position dot normalized. So now let's go here. Try it again. And they all move toward the player and then away from it. We actually want them to move toward the player and stay and not fly away. That means that we actually want to set in our logic, where we are right now, the direction that we want is actually this. Negative of the enemy position normalized. And we can remove enemy direction here. Then we can try it. And they all ran toward us and stayed where we are, which is awesome. This also means that we actually don't even need game data dot enemy direction. We can actually just get rid of it. This whole array can go, because we're going to dynamically calculate it, especially if the player starts moving around. The enemies will have to follow and chase it, so we'll need to set the enemy direction at every frame as the player moves around. So we don't even need that. So we can just remove that array and that data. And awesome, all these enemies are now chasing after us. So now that we have enemies moving toward our player, let's focus on moving the player around the screen. And to do that, we need to add handling input in our board and in our logic, because the input will modify the game data. So the board, for the board, we will add a handle input method, and it's just going to take our in our game data and our balance. And to handle input, we need our we need both the camera to convert from where we click. We want to convert from where we click to local space for the sprites. So first we need to take the mouse input, use the camera to convert it to world position, and then use our sprite parent to convert that into the local position in our sprite parent. And for that, we actually need our camera. So what we want to do is have a reference to our camera. And what we'll do is we'll actually pass the camera in it, and then we will assign our whatever camera we're using. We'll save the reference, and then in game we can also have a public camera and pass it in. And this means that now in our board we can say that our mouse position is input.mouse position, and then we can say that our world position is the main camera dot, nope, we want screen to world point mouse position, and our local position is going to be the sprite parent to inverse transform point world position. And now this is going to be our local position in the sprite parent class. So however much we move in there, that's how much an object will actually move on the screen. So if you go back here, if we move this much, that's how much the player had actually moved in this space, in this sprite parent space, because that's what it's under. We also want to know when the mouse is up, if it moved, and when it's down. So let's add that. Okay. So now, if our mouse is down, we want to save that position so we can know if we moved from where we moved. So let's add here a vector to a mouse down position. Then we can assign it here. If our mouse move, we want to grab the difference between the current mouse position and what the mouse down position was. So we have our difference is going to be the current mouse local position minus the mouse down position. And the player direction is actually going to be the difference normalized. And that'll be the direction that's the direction that we're moving. And when we're in mouse up, we actually aren't moving anywhere So our player direction is going to be 0. And for that, we want to make sure that we already have player direction in game data. So let's set this to game data.player direction. And then here, we're going to do game data equals vector2.0. And we're just setting the direction. How much we move is going to be set by our player velocity, which we set in our balance. One more thing is that we are modifying game data here in board, but we only want to modify game data in logic using static functions which take in data and modify it. So we're going to add two functions here, mouse move, which takes in our game data, and the diff, and we want to say, and also we want to take in mouse up, which just takes in game data. Actually, what we can do here is actually just take in, because who knows what we want to use it for the future. Who knows what we want to use it for the future? We'll have vector2 mouse down position and vector2 mouse current position. And then we can say game data player direction equals mouse current position minus mouse down position dot normalized. And this can do game data player direction equals vector 2.0. And then here in board, instead of these, we can call logic.mouse move game data with mouse down position, mouse local position. Why isn't it's a vector? No, it's a mouse down position. And this will be logic mouse up takes in game data. The reason we don't pass all of this into logic is it's hard to see it here, but basically we have all these branches here, and you really want to percolate branches up instead of having them in a function down. We want each of these functions to be as simple and understandable as possible. And when you have a function that has a bunch of ifs in it, like if this was our function, we would have to read and go, oh, what happens when we have mouse down? What happens when we have mouse move? When we have mouse up? This way, when we have mouse move, we just go ahead and go, oh, on mouse move, this is what we do. On mouse up, this is what we do. It makes it a lot easier and clearer to see. This is a very simple example, so it's kind of harder to see it here. But if we had like, a 100-line function with a bunch of ifs in it, it makes it really hard because you have to read every single if and think, okay, what is my branch here? Am I going into this if, or am I going into this else, or what is happening exactly? Which really makes it harder to read code and understand code. So now we have our player direction. Let's handle it in tick. So now our tick function is going to do two things. It's going to move the enemies, and it's going to move the player. So let's take this code, and let's actually change it to be its own function. Its own method, and we're going to call it move enemies, and then we'll have another one, move player. And instead of moving the player, our player is always going to be in the middle of the screen. So we're going to be moving the enemies around the player. This is also really great because all our positions, the vector 2s, which use floating point, And if we kept moving in the same direction for a long time, and we actually moved the player, that means that the position of the player, the floating point numbers will get bigger and bigger and bigger. And the bigger a floating point number is, the less accurate it is. By always having the player in the center and moving the enemies around the player, we can ensure that our floating point numbers are very small and our precision is very high, which is much better for games. A lot of games do this. It's actually really bad that Unity Physics doesn't do this. And then if you want to use Unity Physics in a really big world and keep running, like if you have an endless runner, at some point you'll get to really big floating point numbers, and the physics will start getting wonky. And then you have to do crazy stuff like reset the player, or you're limited in how big you can make your levels. So let's implement our move player now. We're going to cycle over all the enemies, and we're going to update their enemy position. So first we want to change the player position based on its direction. So it's going to be game data.player direction times the balance player velocity times the delta time. And then however much we moved is the player position, because we moved from 0 to this new position. So like if you think about it, if we moved from here to here, well, actually this is how much we moved from 0 to player position. So we can now take our enemy position and subtract this player position from it. And that will make it so our enemies are moving instead of the player. But it will look to us as if the player is what's moving. And in board, we want to call our handle input class. We actually want to call the handle input first. So we're doing some input, then based on the input, we're doing logic, and then we're visually showing everything. Let's see what this looks like. And we crashed. Why did we crash? Let's go to the first error. We didn't assign the camera. So let's take the camera and assign it. Let's try it again. And now you can see I can move the player around and all the enemies are chasing me. Now when we move the player around, when we move our player around, the enemies are following us. But they're not colliding with each other, which means that they all end up being in the same spot. So what we're going to do is we're going to add enemy-to-enemy collision. To do that, we're going to implement that collision in our logic class. So instead of, after we do move enemies, we'll add enemy-to-enemy collision. So we're going to call this class handle enemy to enemy collision. And we're going to pass in our game data, and we're going to pass in our balance. Game data and balance. And what we need from the balance, we need to know how big each enemy is. And if we had a bunch of enemies, this is something designers would set. They'd say, oh, this is a big enemy, it's a small enemy. We only have one enemy, but let's add here an enemy radius value. And if we look at it, if we look at our enemy, it's 0.2 is the size. So we're going to make our enemy radius 0.1, because that's half of 0.2, which is the diameter. And now in our logic class, what we'll do is we're going to cycle through all our enemies. We're going to check every enemy against every other enemy and check the distance between them. And to do that, we have to take our radius and actually find the diameter, which is going to be twice that, it's basically going to be a radius plus another radius. So we're going to have float diameter equals balance balance.enemy radius plus balance.enemy radius. And when you calculate the distance between 2 points, it's actually the square root of the difference. But we don't, square root is a very costly operation. So instead, we're going to check the distance against the diameter squared to save that square root. So we're going to have another variable, diameter square, which is going to be our diameter times diameter. And now we can go through all of our enemies. And so for every enemy, we have to check against every other enemy. So we're going to say for every enemy, check for every other enemy after it. So j equals I plus 1. And the vector 2, the difference between them is going to be exactly that, game data.enemy position from enemy I to game data.enemy position enemy j. And what we want to do is, once we actually know whether they are, well, first let's check actually if they're colliding, which we're going to do that using the square magnitude of the difference. So if diff.square magnitude is smaller than our diameter square, then we know we actually have a collision. Smaller equals, because even if it's equals, we're still colliding. Now what we want to do is find the midpoint between the two enemies that have collided, so we can find the collision point, and then we're going to move them in the opposite direction from that midpoint. So the midpoint is going to be the average of the two positions. So we'll take the two positions, add them up, and divide by 2. And now we have the midpoint. And now we want to move each enemy away from the other enemy. So we have our first enemy. It's going to actually, its new position is going to be the midpoint. This one will be times, and we want to have the normalized difference. So we'll have float diff normalized equals a normalized one. Sorry, it's actually a vector 2. Times diff normalized times the radius. So we moved it in that direction, in one direction, and this one, enemy j, is going to be minus. Actually, what we can do here is call this one enemy index 1, and we'll call this one enemy index 2. Okay, so now in theory, we have two enemies that are colliding. We've detected the collision, we got the midpoint, and we moved them both away from each other based on the midpoint. So now, after moving the enemies, we can do handle enemy collision and have the balance in here. Now let's try it out. And we can see now that all our enemies are staying away from each other. And if they show up, they're all crowding around us. So now we have our enemies spawning in a square around us, and they're all chasing us. Let's have them spawn around in a circle instead. So what we'll do is we'll go back to our logic class, and we're going to add another function called spawn enemy. which will take our game data and balance. Let's put it above because that's what we're going to do initially. And so basically what it means is that right here in our start game, instead of calling start game, we'll call spawn enemy instead. And to spawn the enemy, we want to have the circle, so we want to have some sort of spawn radius. So let's go to our balance and add spawn radius to it, which we'll use. And we want to be able to take, to do it in a circle, which means we're going to take a vector and rotate it. So we need to have another function called rotate vector. What rotate vector is going to do is going to take in vector 2, and it's going to take in an angle, and it's going to return a vector 2. Call this A. So what we'll do is we're going to use math sinus and cosinus, and for that we need radians. So first we need to take our angle and convert it to radians. So we're going to create basically a degree to radians value, which takes math.pi and divides it by 180, and we're using double for added accuracy. And then we have our radians is going to be our, let's just change this to degrees, is going to be degrees times degree to radians. Now that we have our radians, we take the cosinus and the sinus, and now we convert the two our vector. Let me double check that. And now we return our vector. So this should allow us to rotate a vector based on these degrees. And I added something by mistake. Oh, we added system, so now we need to have, oh, we're not even using this anymore. We're going to use simply spawn enemy. Awesome. So now we're going to spawn an enemy in a circle around us. So we're going to take our, we're going to take the up direction. Let's call it up. New vector 2. This is 0.0f, 0.f. And now we're going to rotate it randomly in 360 degrees. Random dot value times 6.f. This will give us an angle between 0 and 360. And now our direction that we're going is basically going to be up times angle. Now that we have a direction, where we're going to actually spawn it is going to be based on the spawn radius. So actually we don't need the game data. We're going to return basically the, actually what we'll do is we'll take the game data, we'll take the enemy index, and then what we're going to do is we're going to say the position, the this enemy is now going to be the direction dot normalized times the balance dot the spawn radius. And then here we're going to pass I, because this is the enemy we're going to do. We're going to spawn. Let's try it out. Oh, wait, I didn't, one thing I forgot is I did not, it's not times angle, it's rotate vector, up and angle. Okay, now let's try it. Oh, I did not set the spawn radius. Let's set it to something like 7, because if we take our player and we move it, this is like 5.37, but then we have to beat an angle, so let's make it 7. Just double check. We're gonna start game. We're gonna spawn all these enemies, and we set the position. Let's try it. And you can see all our enemies spawned in a circle around us, and they're all coming up to try and chase us. Now we're going to do one last thing. As the player moves, if an enemy falls off the screen, we want it to respawn, but we want it to spawn ahead of where we're going. So as we're running away from enemies, more enemies will come from wherever direction we're moving. And to do that, we need to check an out of bounds. Is our enemy out of bounds? And if it is, we will respawn it. We'll pass in the balance, and we'll pass in the enemy index. And what we'll do is we'll again check our the distance. We have to check a distance well beyond that. If the enemy is that much farther than the player, we'll decide it's out of bounds. And we already have our spawn radius, and we should be moving toward the enemies, so we can just use that. We can use balance.spawn radius times balance.spawn times balance.spawn radius, because we're doing a square, and we'll increase by like 10%, just so our enemies don't spawn and disappear immediately if they haven't managed to move toward us. And actually, we won't take the enemy index. We're going to loop over all our enemies here. And basically, because our player is always in the center, the enemy position is from the origin, which is where the player is. So we can just take the enemy position dot square magnitude, and if that's bigger or equal to our distance square, then we should spawn this enemy. And that should be enough for us to actually spawn the enemies where we want. We'll do that right after we move the enemies. So let's do game data and balance. But we need to do one more thing. When we spawn the enemies, right now they're spawning in a circle, we actually want to use the player direction to decide where to spawn to. So what we'll do is we'll check the game data.player direction. If the magnitude is bigger than 0, it means we're actually moving. So if our game data player direction magnitude is actually, if it's equal to 0, then we're doing what we already want to do. If it's not, then our direction is actually the player direction, and the angle is actually going to be, we want to be like in an arc. So let's do something like a 180-degree arc. So we want to do from negative 90 degrees to 90 degrees. So we're going to take the player direction and rotate it randomly between negative 90 and plus 90. And then actually, we can now call, hang on, I did not do this correctly. This one is going to be called in both. So we can do a float angle here. And we can do a vector 2 direction. We can define these here. And I think that should work. So as we're moving away, and enemies are showing up. They're not really showing up that randomly though. They kind of seem to be showing up in a line. Let's take a look for a second why that's happening. No, we forgot to rotate based on this. So actually we can do is do quality direction equals this, and then we'll actually call this direction over here. Do the rotation to both of them. So here direction is set to up, here direction is set to player direction. This one, it can be in a full circle, this will be in an arc. Let's try now, and let's, just to make things easier, let's, in our balance, set the player velocity to be a little bit faster. And now, as we're moving around, this is looking way more like a game. Those enemies are spawning based on where we're going. And to make things more fun, we only have 50 enemies here. Let's make it 500. And this is a lot more interesting. Now we have way more of a survivor game with a lot of enemies chasing us. And we can even try, let's try 2,000 enemies for the hell of it. And now we have a lot of enemies that are all chasing us and we have to run away from them. We don't have any damage or dying in this yet, but we have a lot of enemies that are all colliding with each other. It seems to run pretty fast. We don't have a frame per second counter on this right now, but this looks pretty damn cool. So this is the example of how to build a simple survivor game. We can keep adding to this and do more cool stuff, but for now you can see that all we have is our game. We have a single scene, we have our game loop, we have our board, we have our game data and balance, and we have our logic, which actually modifies stuff. And because all we're doing in the logic is running over arrays, then everything is running really fast because this is what data-oriented design is all about.